We're now going to extend the idea of line integrals to surfaces. So if we've got the double integral over some surface of f ds, this is a capital S, or sometimes in some books is written as d sigma, where this s is the surface area increment. ds is defined in one of two ways. The first is if your surface is given as z as a function of x and y, as we saw in the surface area video. This is given by the partials of of z with respect to x and y squared plus 1 dA, and this dA is either dx or dy depending on the order of integration. Or if the surface was given parametrically, this was given as the two tangent vectors t1 cross t2 dA, where these two tangent vectors are the partial derivatives of our parameterization. We have a second type of integral that we'll look at after an example called the flux integral. Let's do one of these scalar surface integrals first. Let's say we're looking at the double integral over a surface of y plus z ds, where the surface is given by, well, let's give the bounding area of the surface. The surface bounds the region given by x squared plus y squared equals 4. So this gives us a cylinder. Z equals 0 and z equals 5 minus y. So this is our surface, and we want to find the surface integral of this function over the surface here. So this surface is actually in three pieces. If we were to sketch this out, so it's x, y, and z. Well, first up we have this cylinder, x squared plus y squared equals 4. If we were to look at the cross section, this in the xy plane, that's going to give us a circle of radius 2. So the bottom of this surface is given by z equals 0. That's the xy plane. And the top of the surface is given by z equals 5 minus y. So z equals 5 minus y is this plane that cuts along through here. So if we imagine this cylinder coming up along here, this is going to give us this. So we've got, imagine a cylinder, the bottom of which was cut off levelly, and the top was sort of cut off at an angle. So this gives us we've got three pieces to the surface. We've got the actual cylinder part, we've got the bottom of the surface, and then we've got the top, which is, in this case, it's slanted. So that means our integral we'll have to do in three pieces. So we'll do these in order of complexity. First, let's look at the bottom. So the bottom is given by z equals 0. Well, the surface is given by z equals 0, but we also have some constraints on x and y. X and y are kind of free, although they take on every value inside this disk. So while z is 0, x squared plus y squared is less than or equal to 4, because the radius of this disk is 2. In this case, it was given by the original cylinder. So in this case, we can actually say, since z equals 0, this is our actual surface. If we want to go through and find our ds here, ds is going to be very easy to calculate. So this is, well, it's the partial of z with respect to x squared, partial of z with respect to y squared, plus 1 dA. And now if we look at this, the partial of z with respect to x, well, z doesn't depend on x, so that partial is 0. Then the partial of z with respect to y, again, z doesn't depend on y, so this is 0, plus 1 dA. And that radical really simplifies up. Then we get the ds is just dA. So that means that our integral turns into the double integral over that bottom region, which is this disk here in the xy plane, over that bottom region of the function, which is y plus z. But on this surface, on the surface z equals 0, we're going to plug z equals 0 into the function that we're integrating. So this gives us y plus 0 ds. And ds we've just figured out is dA. Okay, so now we've got the integral set up. The region of integration is a disk, so we definitely suited to go into polar coordinates in this. So if we change this to polar, we're in the xy plane, so we can make x equal r cosine theta, y equal r sine theta. So our Jacobian, as we've seen before, is r. this gives us, now y will switch over to r sine theta. We multiply by the Jacobian, and then dr d theta. Theta, we're integrating over this disk, so theta takes on the full range of values from 0 to 2 pi. And r, since we're integrating over the entire disk, goes from the center of the disk, r equals 0, to the radius of the disk, which in this case is 2. So since our limits are constant and our function factors up, we can use the box theorem. We write this as the integral from 0 to 2 pi sine theta d theta, integral from 0 to 2 of r squared dr. And this first one is actually 0. The integral of sine gives us negative cosine, which is equal at those two endpoints. So it means the integral along the bottom piece is 0. So of these three surfaces, the bottom one we had zeroed out. So if we look at the, just going to sort of note take off to the side here, the double integral over the surface of y plus z ds is equal to the double integral over the top plus the double integral over the cylinder plus the double integral over the bottom, and this last one we have equal to 0. Okay, so the next one in complexity here is probably actually the top piece. So let's go set up the integral along the top the same way. So as we did before, the first thing we need to do is write down the formula that we have for the top. The top is given by z equals 5 minus y. And again, we want to get parameters for x and y. If we were to look at the shadow of this region in the xy plane, it's actually the same disk that we had before. So while the z is different, x and y have the same relation. We want to have all the x and y values in the disk of radius 2. So x squared plus y squared less than or equal to 4. So first up, to get ds, this is given by our partial derivative formula. Partial z with respect to x squared, z with respect to y squared plus 1 dA. And our partial of z with respect to x, well, our surface, z doesn't depend on x, so that's 0. The partial of z with respect to y, in this case, is negative 1, which is squared, plus 1 dA. So for our ds, this gives us a radical 2 dA. Well, now that we've got this set up, we're ready to write down our integral. So the double integral over the top of y plus z ds is given by double integral over the top. Well, let's actually plug in our function, our x's and y's, plug in all the information we have right now. So first, since we're going to be trading in this ds for dA, the region that we're integrating over, originally this was the surface up on top of the cylinder here, but in terms of x and y coordinates, we look at the shadow of this in the xy plane, and that's the same disk we had before. So our double integral, when we look at this, we look at the shadow, the projection of this in the xy plane, it's actually the region on the bottom. It's the same region of integration we had in the previous problem. And then our integrand, y plus z, this is y plus, z is 5 minus y, and ds is radical 2 dA. So if we simplify a little bit here, the y's will cancel. We're left with 5 radical 2 in the integral, and that's constant, so we can bring it right outside. And then this double integral right here, by definition, is the area of that region of the shadow that we have in the xy plane. And that was the circle of radius 2, or the disk of radius 2. So that means this gives us 5 radical 2 times the area, and the area is pi r squared, and the radius of that disk is 2. So this gives us pi times 4. So that says the integral along the top, the surface integral along the top, is 20 radical 2 pi. So we've done the top, we've done the bottom, now we'll move on to the cylinder, the sides of this thing. Now if we look at the cylinder here, z, this cylinder doesn't depend at all on z, there's no z in here, z is free, so we can't write z as a function of x and y. That means we're not going to be able to use the functional version of this formula, we've got to use the parametric version. So if we parameterize that cylinder, let's go to a new page here. We have that along the cylinder, x squared plus y squared. In this case, x squared plus y squared equals 4, and z is free. So x squared plus y squared is 4, z is free. Well, if we go to parameterize this out then, x, y, and z. Well, x and y equal 4, that just gives us a circle. We can parameterize this, a circle of radius 2. This is 2 cosine t, 2 sine t. Now, z is independent of x and y. So, and it's free, so it gets a parameter, but it gets the other parameter. It doesn't get t, it gets the independent parameter s. So we've got our parameterization. Let's look at our two tangent vectors. And it doesn't matter which of these you take as the first, partial with respect to t or partial with respect to s. I'll do the t's first. So our t1, partial with respect to t, is negative 2 sine t. The partial of y with respect to t is 2 cosine t. The partial of z with respect to t is 0. And then t2, this is the second tangent vector. This is the partial derivatives with respect to s. So the x doesn't depend on s, so its partial is 0. The same with the y, and the partial of z with respect to 0, with respect to s, is 1. So our ds, in this case, we're going to cross these two. This is t1 cross t2 dA. Let's expand that out. This gives us the determinant of this 3×3 system, I, j, k. The first row will be the t1. This is negative 2 sine t, 2 cosine t, 0. And then the second entry, the last entry here is t2, which is 0, 0, 1. So if we go and expand this out, our I component is 2 cosine t subtract 0. The minus j component is negative 2 sine t subtract 0. And then for the k component, we've got 0 minus 0. So that zeroes out. And this gives us dA. So if we write this out, this says that ds, this should be a vector here, that our ds, the first component is 2 cosine t. The second is 2 sine t. And the last is 0. Now this, the ds that we have in the scalar line integral, this ds is not a vector, so this actually gives we have the magnitude of t1 cross t2 for our ds. So the magnitude of this ds is then, well, we take each component, square them, and add them up. This gives us 4 cosine squared t plus 4 sine squared t plus 0. The 4's will come out, and cosine squared plus sine squared is 1, so we get the square root of 4, which is 2. So this gives us 2 dA. Now that we've got the ds in here, let's look at what our limits of integration are. So we're integrating over this surface, this side cylinder here. We want to look at what those parameters range from. So let's just copy the sketch over from what we had before. So we've got this upper cylinder, this upper surface is sort of at an angle from the first one. If we look at the circle values, the values along this disk here, we have the full range of angles, the full range of t values in this case. So t is going to range from 0 to 2 pi. Now if we look at the z's, our surface, our top surface here, was given by z equals 5 minus y. So y, given our parameterization, y was 2 sine t, so we'll plug that into the formula. So our top surface is given by 5 minus 2 sine t. So that's the top surface, and the bottom surface was 0. And since z was s is going from 0 up to this top surface, 5 minus 2 sine t. Those give us our limits of integration. So we're going to integrate from 0 to 2 pi dt, from 0 to 5 minus 2 sine t ds. And then we've got this, this 2 in here that we had before. Now once the 2 is in there, now we've got to put our actual function. If we go way back to the original problem, we were integrating y plus z ds. So this would be y plus z, but y and z we had in terms of these parameters. Right? Y was 2 sine t and z was s. So y 2 sine t and z was s. So now we've got our integral set up. Let's just maybe go and simplify this. This gives us 2, integral from 0 to 2 pi, integral from 0 to 5 minus 2 sine t. And then the function we're integrating is 2 sine t plus s ds dt. Okay, so now that the setup is done, the integral is effectively finished. We looked at the integral along the 3 surfaces, the bottom surface, the top surface, and then the side. The second type of integral we have, the flux integral. This has a lot of applications in physics, especially with electricity. The flux is the vector version of the surface integral. We have here is the integral over the surface of our function. Now this function must be a vector field. So we're looking at the integral of the vector field dotted with the normal vector to the surface, ds, and sometimes this s has a little hat indicated on it. The shorthand we have for this, usually this n hat isn't written. It's understood that this is our that this right here is our there's no vector on this. What we do is we go through and simplify this, because these two will always sort of combine nicely. This will give us f dot ds. We can write this vector s. So we sort of just combine these together. This gives us the direction of the normal vector, and this gives us the magnitude. The two of these together just sort of reconstitute the original ds that we gave in the previous section. So ds is defined here. If we look at this parametrically, this is given by the two tangent vectors, t1 cross t2, dA. And if we look at this as a function of x and y, well, any function of x and y we can rewrite in terms of t1 cross t2. So let's look at an example of this. Let's say we've got the flux over the surface. So we'll write this as f dot ds, where our vector field is, we'll just sort of run with the previous example, although we'll make it a field. So this is 0, y minus z. And our surface will be given by y equals x squared plus z squared, and y equals 1. So it's think of this as the sort of the boundary of some region in 3 space. So if we were to sketch the surface out, y equals x squared plus z squared, it gives us a paraboloid that opens up around the y-axis. And it stops at y equals 1. So we've got this disk at the end that caps the surface off. So this surface is 2 pieces. So we can take this flux integral and rewrite it as the double integral over the paraboloid, f dot ds, plus the double integral over that end cap, the disk, of f dot ds. Well, let's look at each of those pieces in turn. We need a little bit more room than this, so let's look at the parabola first, the paraboloid. So if we look at the double integral over that paraboloid of f dot ds. Well, first we want to look at what the paraboloid is. That was given by y equals x squared plus z squared. Let's go through and parameterize the surface. X, y, z. Well, in this case, x and z are both free, so we could say let x be t, let z be s. If we were to plug those into the formula, we get that y is then t squared plus s squared. And if we want to get our ds, we need our two tangent vectors. So t1, that will be the partial of this with respect to t. The partial of x with respect to t is 1. The partial of y with respect to t is 2t. The partial of z with respect to t is 0. Our second tangent vector, this is the partial with respect to s, is 0, 2s, and 1. So that tells us the ds in this case is, well, this is literally just t1 cross t2. So T1 cross T2 dA. And if we write this cross product out, this gives us the determinant of this 3 by 3, I, J, K. And then for the middle row, we've got T1, so 1, 2T, 0. And then for the second row, we've got T2, which is 0, 2S, 1. So expanding this out, for the I component, we've got 2T minus 0. For the minus J component, we've got 1 minus 0. And then for the K component, we've got 2S minus 0. So that says, and we've got to tack this dA on at the end. So that says the ds is 2t negative 1 2s dA. We've got to do something on here just to make sure we have the right, the correct normal vector. Because unlike for the scalar line integrals, the vector ones, the order of the cross product matters. Because if we were to cross these in a different order, we'd be off by a sign. Anytime we go through and do these flux integrals, we need the outward pointing normal. If our region is closed anyway, which in this case it is, there's no gaps in the surface. The outward pointing normal. Let's take a look at this picture of the region that we had. So that means if we were at some point over here on the paraboloid, we would want the normal that's pointing away from the surface rather than the one that's pointing into the surface. We want the one that's pointing outward. So just to make sure we've got the right sign, let's go through and pick a point for T and for S. We want something that's easy to see, maybe something right near the edge here. So what we'll do is we'll pick something along the top, maybe where Z is a large value, maybe Z is 1 and X is 0. That will be this point right here at the edge, and this should be pointing straight upward. So if we were to plug in, so at this point that we're looking for right here, this is at the point, this is X, Y, Z. So at the point X equals 0, Y equals whatever the Y value is, and Z equals 1. So we need 0 for the X value, 1 for the Z value. So 0 for the X value, 1 for the Z value. So we want to plug in T equals 0, S equals 1 into the formula for our normal vector. Make sure it's pointing in the right direction. If we plug that in here, we've got, well, you plug in T equals 0, we've got 0. You plug in S equals 1, so 0, 1, 2. So is this pointing in the right direction? So 0, 1, 2 is pointing upward, which is exactly the direction we want this thing to be pointing in. So this is pointing upward. We know that we've got the right ds on this. And if it wasn't, that means we just cross these in the wrong order, and we would just throw a negative sign on here to fix it up, make sure it's in the right order. So we've got the ds. Let's now write out our parameterization. Well, let's look at the values for x and t to get our limits of integration. We'll do that maybe after we put the function in. Our f was given by 0, negative y, z, dot. ds, well, that was given by this this vector we had right here, 2t, negative 1, 2s. If we go through and expand this dot product out, the 0 and the 2t zero out. Negative y times negative 1 is y, plus z times 2s is 2sz. dA. So now let's replace these and look at our limits of integration. So y, well, y is given by t squared plus s squared. Z is given by s, so this is 2s squared. And dA is ds dt. Now if we look at our limits, well, we've got to go back to our picture to get an idea of what the limits of integration are. If we look at the shadow of this thing in the xz plane, because x and z are the independent variables in this case. If we were to look at the shadow of this in the xz, that's actually just giving us this disk sort of pushed back along that plane. So that's giving us this disk of radius 1. So that means that the t values are going from negative 1 to 1, and the s values from negative square root of 1 minus t squared to positive square root of 1 minus t squared. So rather than integrating with these crazy limits in here, let's go to polar. So if we go to polar, well, we sort of have a choice over which of these two variables plays the role of the x, which plays the role of the y. Let's just say s equals r cosine theta, and t equals r sine theta. Then our Jacobian will be r. So if we write this out, this gives us, well, t squared plus s squared is, that's s squared plus t squared gives us r squared, plus 2. Now, s is given by r cosine theta, so this gives us 2r squared cosine squared theta. Then we've got the Jacobian, r, dr d theta. We're integrating over the disk, so our limits of integration as far as theta goes, we've got the full range of angles from 0 to 2 pi. And then for r, we've got a full disk worth of values from the center of the disk out to the outer radius. So that's going to be the setup of the integral along the parabola. Let's look at the integral along the disk. So if we go and look at that double integral over the disk of 0 minus y z dot ds. Well, on that disk, let's just sketch out that picture again. So we've got this disk over here. Our disk was at y equals 1, and x and z sort of free, although they're constrained inside the unit disk there. So now again we can parameterize this disk, x, y, and z. Well, the easy part is y. That's got to be 1. So the x and z are tracing out all the values in this disk of radius 1. So that means we can actually think of this, we can parameterize this in terms of polar. X is r cosine theta, z is r sine theta. So now let's look at our ds. To get the ds, we want our two tangent vectors. So t1, that would be the partials of this thing with respect to your variable of choice. Let's look at the partial with respect to r. So this gives us cosine theta, 0 sine theta. T2, these are the partials with respect to the second variable, which in this case is theta. So the three partials with respect to theta are negative r sine theta, 0, and r cosine theta. So then ds is then the cross product of these two. So if we expand that out, our top row I, j, k, the middle row cosine, 0, sine, and then the bottom row minus r sine theta, 0, and r cosine theta. We expand this out. In the I column, we've got 0 minus 0. In the j column, cosine times r cosine is r cosine squared theta. In the k, we're subtracting sine times negative r sine, which is negative r sine squared. And then a k component, we've got 0 subtract 0, which is 0. So if we simplify this, the I and the k are gone. In here, we can cancel these minus signs, factor out the r, and this gives us r, no vector r, j. And now this was ds, so we have rj dA. So if we now write that double integral out, the double integral over the disk of, well, we have 0 minus y z dot ds, so we're dotting this with rj. So this gives us the double integral. We dot product this out. There's only one component in this vector. The I component here is 0. The z component here is 0. So we dot these together. We get minus y r dA. Now on this surface, the y on the surface is 1. So we're going to plug that 1 in for our y value. So this gives us the double integral over this disk of minus r dr d theta. And if we look at the limits of integration, if we go back up and look at this parameterization here, this is just the standard polar parameterization. So again, theta goes from 0 to 2 pi. R goes from 0 out to the edge of the disk at 1. Means we can take that 1 out. We can use the box theorem on this. 0 to 2 pi of d theta. 0 to 1 of r dr. This first integral right here gives us 2 pi. The second one gives us r squared over 2. Evaluate those endpoints as 1/2. So we've got negative pi for that integral through that end cap, the disk at the end of that surface. So we add those two pieces together, that gives us the flux across the surface. So we'll have a chance to look at more of these in detail in class.